A deep dive into the Node.js event loop for the advanced technical interview. Part 1. The foundational model. How a single thread does so much. At the heart of Node.js lies a design that appears paradoxical. It is renowned for its ability to handle immense concurrency, serving tens of thousands of simultaneous connections. Yet it operates on a single thread. Understanding how Node.js resolves this paradox is the first and most critical step toward mastering its architecture. The answer lies not in doing more work at once, but in a philosophy of never waiting for work to be done. This is achieved through an event-driven, non-blocking I/O architecture, which is the cornerstone of the Node.js runtime environment. The core paradox: concurrency without parallelism. When discussing Node.js, the term single-threaded refers specifically to the execution of the user's JavaScript code. There is only one main thread, and therefore only one piece of JavaScript code can be executed at any given moment. This means Node.js does not achieve concurrency through the traditional model of creating a new thread for every incoming request, a model that can be resource-intensive and difficult to scale. Instead of parallelism, where multiple tasks run simultaneously on different CPU cores, Node.js employs a model of concurrency based on efficient task switching. It excels in applications that are I/O bound, meaning the application spends most of its time waiting for operations like network requests, database queries, or file system access to complete. Rather than blocking the single thread while waiting for these slow operations, Node.js delegates them and moves on to execute other tasks. When the delegated operation is complete, Node.js is notified and schedules the corresponding callback function to be executed when the main thread is available. This event-driven model ensures that the main thread is almost always busy executing code rather than sitting idle waiting for I/O, making it exceptionally efficient for its intended use cases. The key players: V8 and libuv. The Node.js runtime is not a monolithic entity. It is a composite system built primarily from two powerful independent components: Google's V8 JavaScript engine and the libuv library. V8 engine, the brain. The V8 engine, written in C++, is the component responsible for parsing and executing JavaScript code. It is the same engine that powers Google Chrome. V8's primary responsibilities within Node.js include the call stack, a data structure that tracks where the program is in its execution. When a function is called, it is pushed onto the stack. When the function returns, it is popped off. The call stack is the domain of synchronous execution. It processes one operation at a time in a last-in, first-out LIFO manner. The memory heap, a large, unstructured region of memory where objects, variables, and function definitions are allocated. V8 is engineered for speed, employing sophisticated techniques like just-in-time JIT compilation to optimize JavaScript execution. However, V8 itself does not know how to perform I/O operations like writing to a file or making a network request. Its world is confined to the synchronous execution of JavaScript code. Libuv library, the workhorse. This is where libuv comes in. Libuv is a multi-platform C library that provides Node.js with its asynchronous, event-driven I/O capabilities. It is the component that allows Node.js to be non-blocking. Libuv's key contributions are the event loop. Libuv implements the central event loop mechanism that processes events and executes callback functions. Asynchronous I/O. It handles I/O operations, network, file system, DNS, etc., asynchronously. On different operating systems, it uses the best available mechanism, such as EPOL on Linux, KQ on macOS, or IOCP, I/O completion ports, on Windows, to efficiently monitor multiple I/O sources without blocking. The worker pool. For certain operations that can be CPU intensive, or for which there is no non-blocking kernel-level API, like some file system operations or cryptographic functions, libuv maintains a pool of threads. When Node.js needs to perform one of these heavy tasks, it offloads it to a thread from this worker pool. This prevents the main JavaScript thread from being blocked. When an asynchronous function like fs.readFile is called in Node.js, v8 hands the operation over to libuv. Libuv then uses its worker pool to read the file. Once the file is read, libuv informs the event loop that the operation is complete and places the associated callback function into a queue, ready to be executed. The restaurant analogy. Building a strong mental model. To make this architecture intuitive, especially for an audio format, a detailed analogy of a modern restaurant is exceptionally effective. The waiter, the Node.js main thread. Imagine a restaurant with only one waiter. This waiter is incredibly fast and efficient at their specific jobs, taking orders from customers, delivering those orders to the kitchen, and bringing prepared food from the kitchen to the tables. The waiter can only do one of these tasks at a time. Crucially, the waiter never cooks. If they did, they would be stuck in the kitchen for 10 to 20 minutes preparing a single dish, while a long line of customers forms at the door, unable to even place an order. This is the essence of a blocking system. The customers. Incoming requests. Customers are the incoming requests to the Node.js application, such as HTTP requests to a web server. The kitchen, the libuv worker pool. The kitchen is a separate, highly capable operation with its own staff of chefs, the worker threads. The kitchen can handle multiple orders I/O operations at once. This is where the time-consuming work of cooking, reading a file, querying a database, takes place, completely independent of the waiter's activities in the dining area. The order ticket and pager, the callback and event queue. When the waiter takes a customer's order, they write it on a ticket and hand it to the kitchen. They then give the customer a pager. With the slow task delegated, the waiter is immediately free to attend to the next customer, take their order, and repeat the process. This is the non-blocking nature of Node.js. When a chef in the kitchen finishes a dish, they find the corresponding order ticket and activate the customer's pager. The pager buzzing is the equivalent of a callback being placed into the event queue. The event loop in action. The waiter, after completing a quick task, like seating a new customer, glances at a monitor that shows which pagers are buzzing. If they see a buzzing pager, they go to the kitchen, pick up the finished dish, and deliver it to the correct table. This act of checking for buzzing pagers and delivering the food is the event loop processing a completed callback. This analogy powerfully illustrates the efficiency of delegation. The system's high throughput comes not from the waiter working in parallel, but from the waiter never being idle. By delegating all time-consuming tasks to the specialized kitchen staff, libuv, the single waiter, the main thread, can service a massive number of customers concurrently. Any synchronous long-running code in your JavaScript is equivalent to the waiter stopping in the middle of the dining room to solve a complex puzzle, bringing the entire restaurant's operation to a grinding halt. This is the fundamental cause of what is known as event loop blocking or starvation. Part 2. The execution primitives, a tale of two queues. To understand the precise order in which asynchronous code executes in Node.js, it is essential to move beyond the high-level analogy and examine the specific data structures that govern execution flow. The event loop orchestrates a dance between the call stack and two primary types of queues, the macro task queue and the micro task queue. Their distinct rules and priorities dictate the runtime behavior of timers, promises, and I/O events. The call stack, the realm of synchronous code. The call stack is the most fundamental component of JavaScript execution, managed by the V8 engine. It can be visualized as a stack of plates or a to-do list for function calls, operating on a last-in, first-out LIFO principle. When a Node.js script begins, the V8 engine creates a global execution context and pushes it onto the bottom of the call stack. Every time a function is invoked, a new stack frame containing that function's arguments and local variables is pushed onto the top of the stack. When that function finishes, i.e., hits a return statement or the end of its block, its frame is popped off the stack. The single most important rule governing the entire asynchronous model is this: the event loop can only introduce new work by pushing a task onto the call stack when the call stack is completely empty. This means that as long as synchronous JavaScript code is running, no asynchronous callback can interrupt it. The synchronous code must run to completion first. Macro tasks, the task queue, one at a time. The term macro task refers to any distinct independent piece of work that the event loop can schedule. These tasks are held in what is often called the task queue, or more generically, the callback queue. Sources of macro tasks. Common sources of macro tasks in Node.js include callbacks from setTimeout, setInterval, setImmediate, I/O operations like file reads or network responses, and UI rendering events in a browser context. The initial execution of the main script itself is also considered a macro task. The golden rule of macro tasks. In each iteration of the event loop, the engine will select only one macro task from the queue, push it onto the now empty call stack, and execute it fully. After that single macro task is complete, the event loop does not immediately pick the next macro task. Instead, it first checks the microtask queue. Microtasks, the job queue. Drain until empty. The microtask queue, sometimes called the job queue, is a separate queue that holds tasks with a higher priority than macro tasks. These tasks are typically smaller pieces of work that need to execute as soon as possible after the current operation, often to resolve the state of a promise or update an application state before the next macro task begins. Sources of microtasks. The primary sources of microtasks are promise-related callbacks, .then, .catch, and .finally, the continuations of code after an await expression, callbacks scheduled with queue_microtask, and mutation observer callbacks in the browser. The golden rule of microtasks. The event loop has a different rule for this queue. After a macro task completes and its corresponding frames are popped from the call stack, the runtime will immediately check the microtask queue. It will then execute every single microtask currently in the queue, one after another, until the queue is completely empty. This is a crucial distinction. If, during the execution of a microtask, another microtask is added to the queue, that new microtask will also be executed in the same turn before the event loop is allowed to continue to the next macro task. Process.nextTick: a queue of its own. Node.js introduces a third, even higher priority queue that is specific to its environment, the nextTick queue, populated by calls to process.nextTick. These tasks are not technically part of the libuv event loops phases, but are a feature of the Node.js runtime itself. The ultimate priority, the nextTick queue, has the highest priority of all asynchronous tasks. The callbacks in this queue are processed immediately after the current JavaScript operation completes, but before the event loop continues to its next phase, and, critically, before it processes the microtask queue. The established order of execution priority is therefore synchronous code on the call stack, callbacks in the process, .nextTick queue, callbacks in the microtask promise queue, one callback from the macrotask queue. This strict hierarchy is not an arbitrary design choice. It is fundamental to creating predictable and robust asynchronous APIs. The high priority of the microtask queue ensures that a series of chained promises, as is common with async, await, resolves as a cohesive, logical unit. The steps of a single asynchronous function are kept together, preventing a lower priority macro task like a set timeout fn0 from unpredictably firing in the middle of a promise chain and creating a confusing state. Process nextTick provides an even more immediate deferral mechanism, essential for certain API patterns where a callback must execute after the current call stack unwinds, but before any other asynchronous event is handled. Understanding this priority system is the key to deconstructing and predicting the output of complex asynchronous code snippets, a common task in technical interviews. Part 3. A phase-by-phase journey through the libuv event loop. The Node.js event loop, powered by libuv, is not a single monolithic queue. It is a carefully orchestrated multi-phase cycle. Each phase has its own queue of callbacks to execute, and the loop progresses through these phases in a specific, repeating order. Understanding this deterministic state machine is crucial for reasoning about the timing of different asynchronous operations, particularly timers, I/O, and set immediate calls. A critical point to remember throughout this journey is that between each phase of the event loop, and even after a callback within a phase completes, Node.js will check and drain the nextTick queue, and then the microtask promise queue before proceeding. This means microtasks have the opportunity to execute many times within a single turn of the main event loop. The libuv event loop consists of the following major phases, executed in this sequence. First phase 1. Timers. Responsibility. This is the first phase in the loop's iteration. Its sole purpose is to execute callbacks for timers that have been scheduled with set timeout and set interval, and whose specified time threshold has now passed. How it works. The timers are not stored in a simple queue, but in a more efficient data structure like a min heap, which allows libuv to quickly find the next timer that is due to expire. When the loop enters this phase, it gets the current time and checks the timer heap for any callbacks whose scheduled execution time is less than or equal to the current time. These expired timer callbacks are then executed sequentially. It is important to note that the callback is not guaranteed to run at the exact millisecond specified. The delay is a minimum delay. The actual execution can be deferred by the operating system's scheduler or by long-running operations in previous event loop cycles. Second phase 2. Pending I/O callbacks. Responsibility. This phase executes certain system-level I/O callbacks that were deferred from the previous loop iteration. For example, if a TCP socket receives an EA gain error when trying to connect, instead of executing the error callback immediately within the poll phase, libuv might defer it to be executed here in the pending callbacks phase. Developer interaction. This phase is generally for internal libuv operations. As a Node.js developer, you will rarely, if ever, interact with it directly. It is mentioned for completeness, to provide a full picture of the libuv cycle. Third phase, 3 and 4. Idle, prepare, internal. Responsibility. Similar to the pending callbacks phase, the idle and prepare phases are used internally by libuv for its own housekeeping purposes. The prepare handles, for instance, have their callbacks invoked just before the loop is about to block for I/O in the poll phase. Developer interaction. These phases are not exposed for general developer use in Node.js and serve internal functions within the C library. Fourth phase 5. Poll. Responsibility. The poll phase is arguably the most important and complex phase of the event loop. It is where the majority of I/O related work happens and has two primary responsibilities: calculate timeout and block for I/O. The loop determines how long it should wait for new I/O events to occur. It calculates this timeout based on the nearest scheduled timer. Then, it will block, waiting for events, like a network socket becoming readable or a file operation completing. This blocking is what allows Node.js to be idle and consume minimal CPU when there is no work to be done. Process poll queue. Events. Once the loop is unblocked by a new I/O event, or if there were already completed I/O events waiting, it will process the queue for this phase. This queue contains the callbacks for most completed I/O operations, such as the callback from an fs.read file or an incoming HTTP request handler. Phase 5, Phase 6, check. Responsibility. This phase is dedicated to a specific Node.js function, setImmediate. All callbacks scheduled using setImmediate are placed in the check queue and are executed during this phase. Timing. The check phase runs immediately after the poll phase completes. This ordering is the key to the deterministic behavior of setImmediate when used within an I/O callback. Sixth phase, 7. Close callbacks. Responsibility. This final phase in the iteration executes callbacks for handles that have been closed. For example, if a socket or stream is abruptly closed, e.g., socket.destroy, the close event callback will be fired here. This phase is primarily for resource cleanup. After the close callbacks phase, the event loop completes its iteration. If there are still active handles, like an ongoing set interval or an open network server, the loop will start over from the timers phase. If there is no more work to be done, the Node.js process will exit. This fixed deterministic sequence of phases is the foundation upon which all asynchronous scheduling in Node.js is built. By knowing that the check phase always follows the poll phase, and the timers phase is only revisited at the start of a new loop, one can accurately predict the execution order of different asynchronous functions and solve the complex timing puzzles often presented in advanced technical interviews. Part 4. Demystifying asynchronous scheduling. Node.js provides several functions to schedule the execution of code asynchronously. While they may seem similar at first, their interaction with the event loop's phases and priority queues leads to significant and often subtle differences in behavior. Mastering set timeout, set immediate, and process next tick is a hallmark of an advanced Node.js developer. The showdown: set timeout fn0 versus set immediate fn. This is a classic interview topic designed to test a deep understanding of the event loop's structure. The execution order of set timeout fn0 and set immediate fn is not constant. It depends entirely on the context in which they're called. Inside an I/O cycle deterministic. When these two functions are called from within an I/O callback, for example, inside the callback of an fs.read file or an HTTP request handler, their execution order is completely deterministic. Set immediate will always execute before set timeout fn0. The reason for this is a direct consequence of the event loop's phase order. The I/O callback itself runs during the poll phase. After the poll phase completes its queue, the event loop moves to the very next phase, which is the check phase. Since set immediate callbacks are executed in the check phase, the set immediate callback is executed almost immediately. The set timeout callback, however, is scheduled for the timers phase. The timers phase will not be revisited until the event loop completes its current full cycle and starts a new one. Therefore, set immediate wins the race every time in this context. Outside an I/O cycle, non-deterministic. When set timeout fn0 and set immediate fn are called in the main module of a script outside of any I/O callback, their execution order becomes non-deterministic and is bound by the performance of the process. This seemingly random behavior stems from a subtle race condition at the start of the Node.js process: timer clamping. When set timeout is called with a delay of 0, Node.js internally clamps this value to a minimum of 1 millisecond. So, set timeout fn0 is effectively set timeout fn1. Process: startup. When the script runs, the main module code is executed. The set timeout is scheduled to fire after 1 millisecond, and the set immediate is scheduled for the check phase. The race. The event loop then begins its first iteration. It must first enter the timers phase. To do this, it checks the current time to see if any timers have expired. The non-determinism arises from the amount of time it takes for the Node.js process to initialize and reach this first check. Scenario A. Set immediate runs first. If the process startup and initial script execution are very fast, taking less than 1 millisecond, when the event loop enters the timers phase, the 1 millisecond timer for set timeout has not yet expired. The timers phase will find nothing to do and will move on. The loop will proceed through the subsequent phases until it reaches the check phase, where it will execute the set immediate callback. The set timeout callback will then run on a later turn of the event loop. Scenario B. Set timeout runs first. If the process startup is slightly slower, perhaps due to load on the machine, and takes more than 1 millisecond, then by the time the event loop enters the timers phase for the first time, the 1 millisecond timer has already expired. The timers phase will execute the set timeout callback. The set immediate callback will then run later when the loop reaches the check phase. Because the startup time of the process can vary, the order is unpredictable when run in the main module. Process.next tick, the highest priority deferral. Process.next tick is often misunderstood. It is not a simple alias for set timeout fn0 or set immediate. As discussed, it is not part of the libuv event loop at all, but is a Node.js specific feature that operates on its own high-priority queue. The next tick queue is processed after the current operation completes, but before the event loop is allowed to continue to its next phase or even to the microtask queue. This makes it the most immediate form of asynchronous deferral. This has two primary powerful use cases. API consistency, releasing Zalgo. A common pattern in API design is to ensure a function is always asynchronous, even if it can sometimes complete its work synchronously, e.g., by retrieving a value from a cache. If the function sometimes calls a callback synchronously and sometimes asynchronously, it can lead to unpredictable behavior and bugs. This is known as releasing Zalgo, by wrapping the synchronous execution path in process. Next tick. A developer can guarantee that the callback is always invoked on a future tick of the event loop, after the rest of the user's code has had a chance to execute. Allowing event listeners to be attached. A classic example is creating an event emitter that needs to emit an event immediately upon its construction. If this .emit event is called directly in the constructor, it will fire before the user has any opportunity to attach a listener with .onEvent. By wrapping the emit call in process next tick, the emission is deferred until after the constructor has finished executing, giving the user's code time to set up the necessary listeners. While powerful, process.nextTick should be used with caution. Because its queue is processed before the event loop continues, a recursive process. NextTick call can starve the event loop, preventing any I/O from ever being processed. The Node.js documentation itself recommends that developers use setImmediate in most cases because it's easier to reason about and interacts more predictably with the rest of the event loop. Table 1. Comparison of asynchronous scheduling functions in Node.js. Function queue, type event loop, phase, / timing, priority, key use case / nuance, process.nextTickFN, nextTick queue. After current operation, before event loop continues, highest. Ensure a callback runs before any other async task. Used for API consistency and to allow event listeners to be attached. Can starve I/O if overused. Promise. Then await microtask queue. Between event loop phases, after nextTick, handle the result of a promise. The standard for modern asynchronous control flow. Ensures logical steps of an async operation execute cohesively. SetImmediate EFN, macro task, check, phase low, but high priority after I/O. Schedule a script to run immediately after the poll phase completes. Best for tasks that should run after I/O events. Set timeout FN0, macro task timers. Timers, phase low. Schedule a script to run after a minimum delay. The callback will run in the next timer's phase after the delay has passed. Export to Sheets. This table provides a dense, high-value summary that crystallizes the most complex and nuanced part of the discussion. It allows for quick recall of the key differences in priority and execution context, which is invaluable for on-the-spot interview analysis. Part 5. The TypeScript layer, clarity and safety in asynchronicity. While the event loop is a core runtime concept of JavaScript, TypeScript provides a powerful static type system that sits on top of it, fundamentally improving the developer experience and the robustness of asynchronous code. TypeScript does not change how the event loop works, but it provides guardrails and clarity that transform how developers write and reason about asynchronous operations, especially when using promises and async await. Deconstructing async/await. The async await syntax, introduced in ES 2017 and fully supported by TypeScript, is best understood as syntactic sugar for promises. It allows developers to write asynchronous code that reads and behaves much like synchronous code, avoiding the nested callback structures often referred to as callback hell. Async functions. An async function is one that is declared with the async keyword. The most important rule is that an async function always returns a promise. If the function explicitly returns a value, TypeScript and JavaScript will automatically wrap that value in a resolved promise. The await keyword. The await keyword can only be used inside an async function. When await is placed before a promise, it does not block the event loop. Instead, it performs several actions under the hood. It pauses the execution of the current async function only. It takes the remainder of the async function and essentially wraps it in a dot, then callback. This callback is then scheduled to run as a microtask once the awaited promise settles, either fulfills or rejects. Control is immediately returned to the caller, and the event loop is free to continue processing other tasks. This mechanism ensures that while the logic of a single function appears to wait, the entire Node.js process remains responsive and non-blocking. The power of promise in Node.js. The true power of using TypeScript for asynchronous programming in Node.js comes from its typed promise generic. This feature provides a level of safety and clarity that is impossible to achieve in plain JavaScript. Compile time type safety. This is the primary benefit. In JavaScript, a promise can resolve with any type of value, a string, a number, an object, undefined, and you only discover what it is at runtime. This can lead to subtle bugs. In TypeScript, you can declare that a function returns a promise. This is a contract that guarantees, at compile time, that the promise, when it resolves, will yield a value that conforms to the user type interface. If you try to resolve the promise with a value of the wrong shape, or if you try to access a non-existent property on the awaited result, the TypeScript compiler will raise an error before the code is ever run. Improved readability and self-documentation. Strongly typed promises make asynchronous data flows much easier to understand. When another developer sees a function signature like function fetch user data ID string promise, they immediately know the function's inputs and, more importantly, the shape of its asynchronous output, without needing to read the function's implementation or rely on documentation that may be out of date. Enhanced concurrency with promise.all. A common task is to perform multiple asynchronous operations concurrently. Promise.all is the tool for this job. It takes an iterable of promises and returns a single new promise that fulfills when all the input promises have fulfilled. Using await promise.all open bracket, close bracket. Close bracket is a highly efficient pattern that avoids a sequential waterfall of await calls. TypeScript enhances this pattern significantly. If you pass an array of promise to promise.all, TypeScript knows that the resolved value of the combined promise will be an array of user objects, user. It can even handle tuples for heterogeneous arrays, for example, promise.all. User, company, will correctly infer the resolved type as user, company. Ultimately, TypeScript's type system transforms a major class of asynchronous runtime bugs into compile-time errors. In a complex Node.js application, data might flow from a database query, promise, be transformed, and then sent to an external API, promise. In plain JavaScript, a simple typo in a property name during the transformation step would only be discovered when the code runs, potentially in a production environment where it is difficult to debug. TypeScript's static analysis of the asynchronous data flow enforced by promise and the awaited utility type catches these errors during development. Demonstrating an understanding of this strategic advantage shows an interviewer that you think not just about making code work, but about making it robust, maintainable, and scalable. Part 6. Advanced Scenarios and Common Pitfalls. A theoretical understanding of the event loop is valuable, but an expert developer must also be aware of the practical scenarios where this system can break down. The most significant pitfall in the Node.js asynchronous model is event loop starvation, a condition where the event loop is prevented from processing tasks in a timely manner, leading to an unresponsive application. Event loop starvation, the silent killer. Event loop starvation occurs when a long-running task monopolizes the main thread, preventing the event loop from proceeding to its other phases to handle I/O, timers, and other events. This can manifest in two primary ways. Cause 1. Synchronous blocking. This is the most straightforward cause of starvation. It occurs when a piece of synchronous JavaScript code takes a long time to execute, blocking the call stack and thus blocking the entire event loop. Examples include heavy computation, a long, complex for loop, intricate data transformations on large arrays, or synchronous cryptographic operations. Crypto.pbkkdf2 sync. Synchronous I/O, using synchronous file system methods like fs.readFileSync or fs.writeFileSync. These methods block the entire process until the I/O operation is complete, defeating the primary purpose of using Node.js. Inefficient regular expressions. A poorly written regular expression, especially one susceptible to catastrophic backtracking, can consume CPU for seconds or even minutes on certain inputs, completely freezing the application. This is the waiter solving a puzzle analogy in practice. The main thread is busy and cannot get to the poll phase to handle new network requests or the timers phase to fire scheduled callbacks. Cause 2. Microtask flooding. The insidious cause. A more subtle and advanced cause of starvation comes from the abuse of the microtask queue. This is a critical piece of minutiae that separates intermediate and expert understanding. The event loops rule is to drain the microtask queue completely after each macro task before moving on. If a microtask itself queues another microtask, that new task is added to the end of the queue and will also be executed in the same turn. This makes it possible to create a runaway chain of microtasks that never ends. Consider a recursive function that calls itself within a promise.resolve.then block. TypeScript. Function starve the loop. Promise.resolve. Then. This callback is a microtask. By calling the function again, we queue another microtask. Starve the loop. DAO. If this function is called, it will continuously add new microtasks to the queue. The event loop will be stuck executing these microtasks forever and will never be able to proceed to the next phase, such as the poll phase, to handle network I/O or the timers phase. The application will become completely unresponsive to any external events. This is particularly dangerous because process.max tick depth, a safeguard that used to exist for the next tick queue, was removed in later versions of Node.js, making it easier to accidentally create this kind of starvation loop. A developer might incorrectly assume that because they are using promises, their code is asynchronous and non-blocking. But a long, unbroken chain of microtasks is just as blocking as asynchronous. While true loop. Mitigating starvation. Preventing event loop. Starvation requires a conscious effort to keep the main thread free. Offload CPU-bound work. For any genuinely CPU-intensive task, e.g., image processing, complex calculations, the work should be offloaded from the main thread. The modern solution for this, in Node.js, is the worker threads module, which allows you to run JavaScript in parallel on a separate thread with its own event loop. Use asynchronous APIs. Always prefer asynchronous versions of I/O functions, e.g., fs.readFile over fs.readFileSync. Process data with streams. When dealing with large files or database result sets, avoid loading the entire dataset into memory at once. Use streams to process the data in manageable chunks, which allows the event loop to handle other tasks between chunks. Yield to the event loop. For long-running loops that cannot be offloaded, you can manually break them up and yield control back to the event loop. A common technique is to process a chunk of the loop and then use setTimeout_process next chunk 0 to schedule the next chunk of work. This places the continuation of the task into the macro task queue, giving other events, like I/O, a chance to be processed. A deep understanding of these pitfalls demonstrates a mature perspective on asynchronous programming. It shows that asynchronous is not a magic bullet. True non-blocking architecture requires a deliberate design that respects the event loop's need to keep moving, ensuring that no single task, whether synchronous or a flood of microtasks, can monopolize the single thread and starve the entire application. Part 7. Synthesis, a framework for answering interview questions. Having explored the architecture, queues, phases, and pitfalls of the Node.js event loop, the final step is to synthesize this knowledge into a practical, repeatable framework. When presented with a complex asynchronous code snippet in an interview, a methodical approach will demonstrate clarity of thought and a deep understanding of the underlying mechanics. The following step-by-step mental checklist can be used to deconstruct any event loop puzzle. 1. Identify and execute synchronous code. First, scan the code for all synchronous operations. This includes variable declarations, function calls, console.log statements, and any other code that is not wrapped in an asynchronous callback. This code will execute immediately and in order, populating and then emptying the call stack. This is always the first output you will see. 2. Identify and categorize asynchronous triggers. Next, identify every function call that schedules asynchronous work. Create a mental list and categorize each one based on the queue it will use. Process.nextTick.callback. Place the callback in the next tick queue. Promise.resolve then, callback or await. Place the callback or the code continuation in the microtask queue. Set immediate callback. Place the callback in the check phase macro task queue. Set timeout callback delay. Place the callback in the timer's phase macro task queue. I/O operations EGFs.read. File callback. Place the callback in the poll phase macro task queue. 3. Run the simulation, the event loop cycle. Now begin simulating the event loop's execution, strictly following the priority rules. Step 3.1. Initial execution is done. The synchronous code from Step 1 has finished, and the call stack is empty. Step 3.2. Check the next tick queue. Look at your next tick queue. Is it empty? If no, execute every callback in the queue, in the order they were added, until it is empty. If any of these callbacks schedule more next tick or microtask callbacks, add them to their respective queues. If yes, proceed to the next step. Step 3.3. Check the microtask queue. Look at your microtask queue. Is it empty? If no, execute every callback in the queue in the order they were added, until it is empty. If any of these callbacks schedule more microtasks, execute them in this same turn. If they schedule next tick callbacks, add them to the next tick queue. If yes, proceed to the next step. Step 3.4. Select and execute 1 macro task. The event loop now proceeds to its phases. It will pick one macro task from the highest priority phase that has a ready callback. The phase order is timers. Are there any expired set timeout or set interval callbacks? Pending I/O. Usually empty for these puzzles. Poll. Are there any completed I/O callbacks? Check. Are there any set immediate callbacks? Close. Usually empty for these puzzles. Execute the single macro task you have selected. Any synchronous code inside it runs now. If it schedules new asynchronous tasks, add them to the appropriate queues, as in Step 2. Step 3.5. Repeat the cycle. After the macro task is complete and the call stack is empty again, go back to Step 3.2. Check the next tick queue, then the microtask queue, and drain them completely before attempting to select another macro task. Continue this cycle. Next tick. Micro tasks. 1 macro task. Until all queues are empty and all code has been executed. By applying this methodical framework, you can confidently trace the execution of any asynchronous Node.js code. Explain the output with precision and justify your reasoning based on the fundamental principles of the event loop's architecture. This demonstrates not just memorization, but a true foundational mastery of the Node.js runtime.